All right, so chapter 11 covers intermolecular forces and then phase changes, especially those phase changes between liquids and solids. We will discuss gases as well, but a lot of the chapter focuses on crystal structure for solids. We're going to skip that part of the chapter, and so that's sort of right in the middle. And so we're going to do these first couple of sections on phase changes and intermolecular forces and things, and then we're going to skip. We're going to skip all of the crystal structure stuff and pick up at the tail end where they talk more in depth about changes between phases. When we say phases, of course, we know there's three phases of matter, and they are solid, liquid, and gas. I saw a few mouths. It's okay that you muted. Solid, liquid, and gas for sure. Now, if you're a physics-minded person, you might say plasma too, and that's another phase of matter, but we're not going to get into that. Okay. Let me see here. All right. So, as we discuss intermolecular forces, we need to sort of think back to Chem 123 and think first about intramolecular versus intermolecular. Intra versus inter. Which one of those means within?
Intra.
Intra, for sure. And so intramolecular forces are those forces that are within molecules, right? That hold atoms together. And what do we call the forces that hold atoms together?
Bonds.
Start with a B. There's a famous
Bonds.
spy. There we go, bonds. We call them bonds, right? So when we talk about forces within molecules, we're talking about chemical bonds. Right? So those chemical bonds, whether those are ionic bonds or covalent bonds or metallic bonds, right? We talked about all those kinds of bonds last semester. Whatever kind of bond we're talking about, those are intramolecular forces. Okay? When we talk about intermolecular forces, we're talking about forces between molecules. And so we're going to focus on intermolecular forces. We spent all of chapter 9 and chapter 10 talking about intramolecular forces and those bonds and how those bonds connect the different atoms and the strength of those bonds. We did a little bit of bond enthalpy calculations. So we did a lot with the intramolecular forces last semester. Intermolecular forces we're going to focus on here at the beginning of this semester. And so just a quick comparison of these two, intra versus inter. I'm sorry, I have to pause for just a moment. I use a pen tablet to write all these notes on, and golly gee, it is uncalibrated. And so I really need to recalibrate my pen tablet. But the calibrate button is grayed out. Oh, technology. Okay, well, we'll make it work. We'll make it work. We can do this. Okay, so inter versus intramolecular, just in terms of their relative strengths. When we talk about in intermolecular forces, so one of the strongest intermolecular forces, we'll talk about that here in a minute, is hydrogen bonding. And so to go from the water, liquid to gas, right? To do that transition, we're not breaking apart those hydrogen and oxygen atoms, right? We're just breaking apart those molecules. And so that's intermolecular interactions. That takes about 40 kilojoules per mole, right? About 40 kilojoules per mole. Now, if we take that same mole of water and we break apart all those oxygen hydrogen bonds, right? So that's breaking intramolecular, that's breaking those bonds. I'll put intra here. Then that's our bond enthalpy, right? And that is about 930 kilojoules per mole. And so, that's a factor of 20 or something different from one another. And so the intermolecular forces are really weak, relatively speaking, but they're responsible for a lot of important things that go on in our lives we don't really think about. One of the most important things that intermolecular forces do is protein folding, right? And so proteins they're made up of amino acids. Some amino acids are what we call hydrophilic. They like water. Some are hydrophobic. They don't like water. They like oily stuff. And so, in our cells, as those proteins fold, they're going to fold so the hydrophilic amino acids are all on the outside of that protein, because the inside of our cells is mostly water, and the part that likes water is going to stick on the outside. And then that part of that protein, those amino acids that are hydrophobic, are going to all sort of clump together in the middle. So they're away from the water. They're sort of protected from the water by that hydrophilic amino acid layer. And so how those proteins fold up to do their function has a lot to do with these intermolecular forces and whether or not they really like to interact with water or interact with nonpolar compounds. Okay. So when we think about intermolecular forces, there are some ways that we can think about measuring intermolecular force strength. The first of these is sort of what we just talked about, this bond strength. But bond strength is something that's very particular to a given compound. An OH bond in water is going to be slightly different in energy than an OH bond in an alcohol, than an OH bond in an amino acid. And so when we think about intermolecular force, we're going to back out just a little bit and look at broader picture things. And since this chapter talks a lot about phase changes, we're going to look at things like boiling points, we're going to look at melting point, just real quick, so knowing what we know about intermolecular forces and these, what a boiling point, what a melting point is, right? If we have a stronger intermolecular force, are we going to have a lower boiling point or a higher boiling point?
Higher.
That's right, we're going to have a higher boiling point. We have to put in more thermal energy, we have to put in more heat in order to break all those intermolecular forces, all those intermolecular bonds, right? And so for both of these get higher with stronger intermolecular forces. Right? I'm going to abbreviate intermolecular forces, IMFs, just to save a bit of time. Okay. We also have some other ways that we can think about intermolecular force strength, and these are also directly related to boiling and melting points, but they're a little bit more scientific, if you will. They're a little bit more exact. And these are enthalpies. Now we're going to talk about three different transitions, three different phase changes, and each of those phase changes requires some amount of energy. Those energies, remember from chapter 6, we call those enthalpies. And so we have the enthalpy change associated with vaporization, so that's what we call boiling. And so delta H vap is our enthalpy of vaporization. And then we have the enthalpy of fusion. That's the one that's related to melting and freezing. So fusing those molecules together. And then the last one is delta H of sublimation. Sublimation and deposition are the phase changes between solids and gases. So those direct phase change where we skip over water. These enthalpy values tell us a lot about how much energy is required to break those molecules apart in a given substance, and therefore tell us a good bit about the strength of those intermolecular forces. Okay. Feel free to just holler out a question if you have anything as we go through these lectures that are online. So we're going to talk about four broad categories of intermolecular forces, and then we'll run through some examples of go ahead. We'll run through some examples of molecules and try to determine what kinds of intermolecular forces they might have. So the first type that we're going to discuss are dipole-dipole forces. Hopefully from chapter 10, you remember that molecules that are polar molecules have this unequal sharing of electrons, and so we end up with this uneven electron distribution. This region over here where we have fewer electrons, what kind of charge does that have? We have fewer electrons.
Positive?
Yeah, it's going to be a little positive, right? We demonstrate that it's not really a full-on positive charge, but only a partial positive charge by giving it a little Greek letter delta. Right? And so there's a partial positive there. If you took any calculus, you might have seen the partial derivative. They use the same symbol there. Right? And on the other side, where we have more electron density, we have a partial negative charge. Right? So it's not a full ionic bond, right? Where we have a true negative charge on one atom and a true positive charge on the other atom. But these are partial positives and partial negatives that are due to this unequal sharing. Right? And so, again, this is just the unequal sharing of electrons. All right, so those of you that didn't have me last semester, E minus is my shortcut for electrons. All right, now we call this imbalance of electrons, right, this unequal sharing of electrons, we call that a dipole. And there's a dipole in this molecule that runs from the positive side of the molecule toward the negative side. And we reference that with a vector, and we draw it from the positive end toward the negative end. Right? We cross the positive end just so we know that that's the positive side. makes like a little plus sign, and it goes towards the negative end of that molecule. Okay. And we call that our bond dipole. So if there's no unequal sharing, in other words, if we have a non-polar compound, then there would be no bond dipole because the electron density is the same on both of those atoms. Right. So dipole-dipole forces, right? As the name implies, these are intermolecular forces, so IMF, that are between two polar compounds. Okay. A good example of the polar compound is something like HCl. Okay. In HCl, which end, the hydrogen or the chlorine, which end is going to have the partial positive side? And how do we know?
Hydrogen.
Hydrogen's partial positive. How do we know that?
Was chlorine's negatively charged?
Chlorine has a negative charge. That's true. We're
Is it about electronegativity?
absolutely electronegativity is what I'm trying to get at. Yeah, and so this is HCl is sort of on that border between whether or not it's truly ionic or a polar covalent, and so we look at the electronegativity differences to determine that, and we're going to look at electronegativity to figure out which side of our molecule has the partial positive and which the partial negative. And so the chlorine has the partial negative, the hydrogen the partial positive. And so if I have a second HCl molecule, I'm going to line it up such that the hydrogen of my second one is near the chlorine of my first one because, of course, opposites attract. And so that partial plus and partial negative are attracted to one another. The partial minuses want to get away from one another. And so this is true for all polar compounds. HCl is true for water, right? And this is one of the things that helps keep polar compounds in what we call the condensed phase, right? Condensed phase is basically not gas. Liquid and solid are both considered condensed phases because they're held together by these intermolecular forces. Once we're in the gas phase, we really, the intermolecular forces don't play a role because the gas molecules are so far apart. If we do have molecules in the gas phase that are close together that have those interactions, we call those aerosols, and those particles that form aerosols, of course, are not great for us and our health. So we try to minimize those negative aerosols. So that's dipole-dipole. The next type of intermolecular force is, in my opinion, the most obvious kind of intermolecular force. This is going to be an ion dipole, right? So we have two ions, we have an ion and a polar molecule. And so let's just choose sodium here. I'm really going to have to do something about this tablet. So sodium has a positive charge, and if he's interacting with, let's say HCl again, just to keep our example straight, if he's interacting with HCl, which end of that HCl molecule is going to want to be near that positively charged chlorine?
CO.
Yeah, absolutely, the Cl with his partial negative charge. If we had a negatively charged ion, like iodide, that would be just exactly flipped, right? The partial positive from the hydrogen would want to hang out with the negative charge, the negative charge on the iodide. So that's an ion dipole. Again, that's the easiest one in my opinion to think of, just because you have one with a charge and it's going to match up with one end of our polar compound. Right. So here we have water interacting with ions. We have a sodium plus and a magnesium 2 plus. Which of these two do you think is going to be a stronger interaction? The interaction with sodium or the interaction with magnesium?
Magnesium.
Yeah, magnesium is going to be stronger because we have a larger charge, right? There's more positive draw from that magnesium ion. And so this is a stronger interaction. Right? And then our ion dipole interaction with sodium and water is weaker. Right? Now, it's still a pretty strong interaction, but it's weaker than the magnesium interaction. Maybe you talked a little bit about this in chapter 10, but this interactions with water and ions is one of the main reasons that ionic compounds are soluble in water, right? When things want to dissolve, they dissolve because they'd rather interact with water here than interact with the rest of that ionic compound in the crystal. But they can, each ion can interact with more than one water molecule. And so they have that ion dipole interaction, not just once, but many times around that ionic surface. And so as long as the interaction between water and the ion is stronger than the interaction between the ions in that crystal lattice, then it will dissolve and be soluble. That's why one of our rules for solubility rules way back in chapter 4 was that if they have large charges, like aluminum phosphate, where we have a +3 and a -3, those are likely to be insoluble in water because the large charges, they want to stick together in that crystal rather than be separated by the water. Okay. All right. So now we're getting into this territory of intermolecular forces where the molecules themselves don't really have a charge, and they honestly don't really have an imbalance of electrons. And so let's take a nonpolar molecule like bromine, right? Remember bromine, Br2, one of our 7 diatomic elements. And so we've got our bromine here. We've got the same atom on both sides of the bond, and he really doesn't have any side. Neither one of those atoms has more electrons than the other. But we talk in chapter 7 about how those electrons behave as waves, right? They this wave-particle duality, and so sometimes they're particles, sometimes they're waves. It depends on how we observe them. And so these electrons really travel in waves, right? The Schrodinger wave equation explains the motion of the electrons. And because these electrons are really moving all around, they don't just move around the individual atoms and never cross over. They really move all around that molecule. As long as there's a chemical bond in between, those electrons can really move around. And so most of the time, those electrons are pretty evenly distributed. Every once in a while, those electrons will be, maybe there'll be a little bit more density on one side of the bromine than the other. And so when we looked at the dipole example on the previous slide, it was pretty obvious which side was the partial positive, not only from the coloring, but because the sort of the bulb, that electron density around one side was much larger. Here, I'm going to try to draw it larger on one side than the other, but in reality, it's not so much larger, right? Maybe just one of those electrons in bromine has shifted over and is, you know, as it travels in a wave, that there's just one extra on one side than the other for a split moment. Right? in that split moment, all of a sudden, this bromine over here, which has a little bit more electron density, has this partial negative, and this bromine over here feels a little bit of a partial positive. This wouldn't be so exciting if we were talking about bromine molecules that are in the gas phase, that are very far separated from one another. But if I have liquid bromine, bromine's a liquid at room temperature. If I have liquid bromine and one of these bromine molecules does this, well, he's right next door to another bromine molecule. And what's going to happen to that bromine? Well, if he sees a partial negative from his neighbor, the electrons in the bromine are going to try to scoot away from it. And so you end up getting the same phenomenon happening in your neighboring bromine molecule. So we have another bromine next door. Oh, he sees that partial negative, and he's going to, his electrons are going to shimmy around so that they sort of match his electron distribution. And you'll have a partial plus over here, and you'll have a partial minus over here. Again, these are not very big differences. These are the weakest of our interactions. And there are lots of things that can induce this, this dipole, right? And so if we have two nonpolar compounds like this, then we call these dispersion forces. Sorry. Ooh. You might have heard another name for them. You might have heard London forces or London dispersion forces. And you might have also heard the term van der Waals forces. Which we often abbreviate VDW. And so all of these are when we have these induced dipole interacting with another induced dipole, right? And so we're going to call these are between nonpolar molecules. So we had dipole-dipole interactions between polar molecules. We had ion-dipole interactions between ions and polar molecules because they had to have a dipole. And now we've got induced dipole interactions between nonpolar molecules. Now, this that I've shown here, dispersion forces or van der Waals forces, that's exclusively between two or more nonpolar molecules. But anything could induce this dipole, right? If I have an HCl molecule nearby to a bromine with his partial minus here and his partial plus here. Well, if I've got a bromine next door, oh, this drives me crazy. I promise I have better handwriting than this. It might not be much better, but it's better than this. So if I have this bromine, this nonpolar bromine molecule next door to an HCl, right, the electrons, are they going to want to go toward that chlorine or away from that chlorine? Away, yeah, because electrons are negatively charged, that chlorine has a partial negative, and so we're going to end up with this induced dipole situation in that bromine, right? And so this one doesn't have sort of an official name, but we know that polar compounds like HCl have dipoles, and then this bromine has an induced dipole. And so we tend to just say that this is a dipole, induced dipole interaction. And that's between polar and nonpolar compounds. Okay. All right. So let's take a quick example here. Oops. Intermolecular forces between the following pairs: HBr and H2S. HBr, is that polar or nonpolar? Unmute and scream out.
Polar.
Polar. HBr is polar. How about H2S? I know you can't see it on my periodic table, but sulfur is just below oxygen. So H2S is a lot like H2O. Polar or nonpolar? Polar. So we've got two polar molecules. What kind of intermolecular forces are we looking at?
Dipole, dipole.
That's it. Dipole-dipole interactions. I'm just going to use one dipole. Chlorine. Polar or nonpolar?
Non-polar.
Nonpolar. And how about carbon tetrabromide, CBr4?
Non-polar?
Also nonpolar, yeah. Maybe you remember this trick from when we talk about molecular geometry in chapter 10. If you've got a central atom and all of the elements around it are the same and there's no lone pairs, then it's nonpolar. So between a nonpolar and a nonpolar, what kind of interactions are we going to have?
Dispersion.
Yeah, dispersion, van der Waals, however you want to say it. Like I said, there's lots of names for that one. All right. So we have I2, polar or nonpolar?
Non-polar.
Nonpolar. And NO3 minus, that minus tells us that this is an ion. And so we didn't talk about this one specifically, but we can figure it out. What kind of interaction is this? So we have ion dipole between an ion and a polar molecule. This is an ion and a nonpolar molecule. So he doesn't have dipole interactions. What kind of interactions does he have? Oops. He has an induced dipole, right? And so we would call this interaction between an ion and a nonpolar compound ion-induced dipole. Again, that's one of those that doesn't have a fancy name associated with it, but we know that ions and nonpolar molecules are going to behave that way. Right? That negative charge on the nitrate is going to cause the electrons in the iodine molecule to move away from the nitrate, inducing a dipole in the iodine. All right, how about NH3, polar or nonpolar?
Non-polar.
He is polar because he has a lone pair. So ammonia looks something like this. Did you do wedges and dashes? He's got a lone pair at the top, and so all those bond dipoles sort of point in one direction. So NH3 polar, C6H6. It turns out that that's all in a flat ring, and all those dipoles cancel out. Also, if you remember, our threshold for a non-polar bond was 0.4 difference in electronegativity, and that 0.4 difference threshold is so that carbon and hydrogen always form non-polar compounds. So if you have a compound that's just carbon and hydrogen, it's always going to be non-polar. So if we have polar and non-polar together, what did we call that? What was the last example we did on the last slide?
Induced dipole.
Yeah, so that would be a dipole because we have a polar compound, and an induced dipole for the non-polar compound. Okay. So those three types of intermolecular forces are very common. The induced dipole exists in almost every situation. Even if you have a permanent dipole, you can induce a little stronger of a dipole when you're around something that has a charge. And so, these dipole-dipole interactions, induced dipole interactions, dispersion forces, these are all around, right? A more specific case of intermolecular force is the hydrogen bond. And when we think about hydrogen bonds, of course, well, it's going to involve hydrogen. But this is a special type of dipole-dipole interaction because we are still talking about the difference in electronegativity. We're just talking about it in terms of hydrogen. And so this is a special dipole-dipole interaction. Okay. It's got to be between hydrogen and one of the most electronegative elements on the periodic table, right? Remember, electronegativity goes up and to the right. That's our trend. We ignore the noble gases, though. And so the three of the most electronegative elements on the periodic table are nitrogen, oxygen, and fluorine. Right? And so these hydrogen bonds are going to be between hydrogen and either nitrogen, oxygen, or fluorine. Not only are these some of the most electronegative elements we have, but they're also very small, right? Chlorine has a pretty high electronegativity. He's just below fluorine, but he also has this extra shell of electrons, and so he's a bit bigger. Right? The thing about nitrogen, oxygen, and fluorine is that they're nice and compact atoms, and so the charge that they do have is very localized, right? It's very compact, very dense charge. And so the way that it works is that we have to have an actual physical covalent bond, an intramolecular force between hydrogen and one of these three. So N, O, or F has to be covalently bound to hydrogen. It can be any one of those three, doesn't really matter. And then from there, we have a hydrogen bond that's usually represented by 3 or 4 little dots in a row. And that hydrogen bond can be to any one of nitrogen, oxygen, or fluorine. Right? So let's say it has a covalent bond to nitrogen, That doesn't mean that it can only hydrogen bond with nitrogen on the other end, right? It can hydrogen bond with any nitrogen, oxygen, or fluorine on the other side. If you need something to help you remember which elements can hydrogen bond, I just like to say that hydrogen bonding is fun. Okay? And so that's how you can remember which ones hydrogen bond. If you are biologically inclined, hydrogen bonding is the force that holds our DNA together, right? So we have these two long strands of base pairs, right? And those base pairs pair up based on hydrogen bonding. I don't remember which pair has 2 hydrogen bonds and which pair has 3, but the fact that they have different number of hydrogen bonding sites is the reason why they pair up, right? So I don't remember if it's A and T or C and G, the ones that have 3, but they've got, one has 3 ways to hydrogen bond, the other has 3 ways to hydrogen bond, and so they form that hydrogen bond in that particular geometry. The other one just has 2, and so they form their pair based on that hydrogen bonding geometry as well. Okay, so just another different way of looking at it, since we've talked a little bit about these electron density clouds. I just wanted you to see it again. For the water here, we have this oxygen and 2 hydrogens. Between those 2, which one's going to have a partial negative, the oxygen or the hydrogens?
Oxygen.
Oxygen's going to be our partial negative for sure. So here's our partial negative. Water, our partial positive. And so here we have another oxygen. Here we have another oxygen, and he's got a partial negative. And this hydrogen has a partial positive. And here's another hydrogen with a partial negative. And here's another water molecule. We know how he goes. And so even if these weren't hydrogen bonds, these dipole-dipole interactions would exist. But because we've got an oxygen, a hydrogen, and another oxygen, those reds are hard to see, I know, sorry about that. We've got an oxygen, a covalent bond to a hydrogen, and another oxygen. That's a hydrogen bond. Here we've got the same thing. We've got an oxygen covalently bound to a hydrogen, and then we can have this hydrogen bond to another oxygen now. Okay. So we'll do a quick example here. Which of these can form hydrogen bonds with water? With water. So that tells us something, right? We know that water is H2O. And so we have an oxygen that's actually physically bound to a hydrogen. And so he can interact with oxygen, nitrogen, or fluorine. And so this first one, this is dimethyl ether. Can he interact, can he have hydrogen bonds with water? Yes or no? Yes, because he's got an oxygen, right? So we can have a dot, dot, dot to our water. Right? How about CH4? No, there's no fun atoms there. How about F2? Yeah, he can, right? How about COOH? He can for sure. Right? And how about sodium plus? No. COOH can actually interact with water both as what we call a hydrogen bond donor and as a hydrogen bond receptor. So let me just draw H, C, double bond O, O, H. So there's our formic acid. So he can have a hydrogen bond here to water, but he could also have a hydrogen bond here to water, just in a different way, right? Oops, that's not an O. Right? So here he's sort of sharing this oxygen at the top is sharing his lone pair with that hydrogen on the water. Here at the bottom, the oxygen in the water molecule is sharing his lone pair with the oxygen in the formic acid. And so we call those differences in arrangement, receiving or, donating or accepting hydrogen bonds, right? All right, well, that is the last thing we will do today. We'll pick up with properties of liquids and phase transitions on Friday, and see how far we get in terms of phase changes and things like that, okay? Any questions before we head out?
Yes. How do you recommend us to study for the quest next class?
So there's not going to be a whole lot on it, right? This is going to be a really short one. There's going to be, mostly it's going to be Chem 123 review, right? So I could throw up some naming. I could look at some molecular geometry shapes and things like that. But I'm going to try to focus on this intermolecular force stuff. The stuff that is due in Alex on 9:15 on Friday, that's the stuff I'm going to try to focus the quest material on.
All right. Okay. Thank you.
Sure. All right. Well, I hope that you all have a great Wednesday.
Thank you.
Thank
Thank you so much.